contrairement au fait que je vous ai encouragé de mettre vos têtes, de rendre visible vos têtes, s'il vous plaît, coupez vos micros, parce que sans ça, tout est multiplié. Bon, alors, je suis content de vous présenter Stephen Clark. Vous savez déjà tout à propos de lui parce que vous avez lu sa bio. Il nous arrive du Royaume-Uni. Actuellement, il est l'organisme DeepMind. Anciennement, il était à plusieurs universités. Il est informaticien de formation. Il s'occupe souvent avec le traitement des textes et du langage, mais l'ancrage l'intéresse aussi. Et avec ça, je cède la parole à Stephen Clark, which means I hand the wheel over to Stephen Clark.
All right, thank you. So yeah, thank you for this invitation. It's very nice to be giving this talk on grounded language learning, particularly to this audience. So yeah, let's start out with the following question in the context of natural language processing, which is, why do we need grounded language learning at all? And I'm talking about these recent advances that I'm sure you're all familiar with, these very large-scale language models like GPT-3, and these have been making a lot of headlines. So apparently, and I believe a lot of the hype around GPT-3, they're very good at doing things like automatic summarization, machine translation, and apparently some of the summaries are even indistinguishable from those produced by humans. But if we look at some of these headlines, the headline writers have got it wrong, I think, in some fundamental ways. So GPT-3 is nothing like a humanoid. It's nothing like the human brain. And if we look at the robot in the bottom right, it's nothing like that in a very important sense, which is that even though GPT-3 reads a lot of text and reads it very quickly, of course, it doesn't have a body, it's not situated, and it's not in an environment. Now, why is all this important, this notion of connecting words to the world and, of course, grounding? Well, so here I'm going to take us back to Stephen's original paper. I'm not doing this because I've been invited by Stephen. I've given this talk a few times now, and I always have this slide. So you won't need reminding, but just briefly, if you remember what Stephen asked us to think of in that classic paper, is to imagine that we're trying to learn Chinese as a second language speaker, and all we've got access to is a Chinese dictionary. Then you immediately see the problem. And I really like this, this metaphor or analogy of the merry-go-round, which is that I've got this symbol or sequence of symbols. I don't know what it means, so I go and look it up in the dictionary, and all I've got, of course, in the definition is more symbols, and round we go. Now, I like this way of thinking about things from the perspective of a large-scale language model, because arguably GPT-3 is on the merry-go-round, and it's not grounded at all. It doesn't act, it's not situated or embodied, it doesn't have an environment. So in fact, I think we can take, if we think that grounding is necessary to do tasks like summarization and translation, and I'm not claiming that that was one of the claims in Stephen's original paper, but people do say that, then I think you can take GPT-3 as a counterexample to that argument. It appears that actually you can do some extraordinary things with text without being grounded at all. So just pushing on a little bit with the philosophy, here's some quotes from, recent quotes from David Chalmers, who's a well-known philosopher of mind. And as he says here, the big question is understanding. And obstacles arise in GPT-3's case because it does many things that would require understanding in humans, but crucially, it never connects its words to perception and action. And then he asks this crucial question: can a disembodied, purely verbal system be said to understand, or is it just on the roundabout, making connections among symbols? Now, just to finish this part off, I'm going to have a rather mundane answer to the question, actually, whether we need grounding, which is that apparently, if you want to do text-only tasks, if your goal is summarization or translation, you can get an awful long way without grounding at all. I mean, it's an interesting question to think whether in the future, when we've got grounded systems, whether they could actually do better at translation. I mean, you can always keep moving the goalposts. Maybe Google Translate's not very good at translating Persian poetry at the moment, for example. So if your goal is just text, apparently you don't need grounding. But my goal is something else. So at DeepMind, we have this notion of what's become known as AGI, or artificial general intelligence. It's just another name for AI, actually. It just means, we're not going to focus on one particular modality like language or vision. We want sort of human level AI. So if that's your goal, and if we think in terms of applications here, I've got what you can think of as the ultimate Alexa. It's a robot that cooks breakfast for you, drives the kids to school, plays the piano, maybe teaches the kids piano, maybe it can write Persian poetry. Then in this case, it just seems absolutely clear that the language use of the robot has to be grounded. There's just no other way that you could communicate with it. So that's one strong motivation, I think, even in the light of GPT-3, for still thinking about grounded language, and that's ultimately what we care about. Now, just having a chat with Stephen earlier about different forms of language grounding, so maybe we could perhaps stop in a minute and see if there are any more questions and comments on this section. But here, what I normally do is say that there are different ways of doing grounding. So the one that we really care about is in the top left. That's sort of the gold standard. That's grounding in the real world. Oh, and incidentally, just as an aside, I'm not going to provide a definition of grounding in this talk. I think I've got one at the end as some bonus slides, but I'm sort of relying on all our intuition about what it means for a word to have some reference in the world. That's really what I'm talking about. And the gold standard reference or grounding is in the real world, like we've got with this robot talking to the child. But I normally say that I'm quite happy with the idea of grounding captions in videos or images. One use of grounding I'm perhaps not so happy with is what we used to call grounding in NLP, actually, sort of 20 years ago. And maybe it's still used this way. People talk about grounding in databases, for example. So the idea of grounding here would be that you have some semantic parser, produces some logical expression, and you execute it on the database. So that execution is meant to count as the grounding. That makes me a little nervous because the database is just more symbols. And I don't think you can't ground symbols. I'm getting a little bit of noise there coming through. We're still okay.
Can I ask everyone to turn off their sound? And maybe, maybe I shouldn't have asked for so many people to turn on their faces. It may be taking too much bandwidth. So if you were uncomfortable showing your face, you can take it off now. Go ahead, Steve.
All right, thank you. Yeah, so what we're ultimately concerned with is grounding in reality, but for all the reasons we're familiar with, the robotic technology is not where we need it to be. One thing I've learned at DeepMind is that robotics is really hard. So what we're going to do instead in this talk is ground in simulation. Now, clearly there's a gap. So if I just sort of go back, I'm meant to be showing the sim to reality gap here. And the simulation we have is so far removed from reality in many ways. But we think that there are some aspects that make it better than videos and images, and in particular, the fact that the agent in our environment can interact with its world. It can pick up objects and move them around. And that's we think that's important for doing grounded language learning. So yeah, maybe I'll just stop there and see if there are any comments about that opening sort of philosophical section around grounding.
All right. On peut poser des questions en français ou en anglais. On peut les traduire. Casey, I want to present you because Casey Kennington already gave a talk, and he's coming in from. Where are you right now, Casey?
I'm in Idaho, still in Boise, Idaho, in the United States.
Okay. Yep. So I expect that Casey will probably have a few things to say about what you're talking about. I just wanted to ask you, since we presumably both accept the Church-Turing thesis that just about anything can be simulated in a virtual world, why isn't simulation enough for real grounding? Or is it enough for real grounding?
Oh yeah, I think it probably is. My point was only a practical one that at the moment the simulations just aren't very good. That's all. So there's you could argue that the simulations are so trivial at the moment that sort of reverse engineering the underlying game engine is somewhat trivial to reverse engineering the physics of the world, which is presumably what we'd have to do eventually. That could be one argument. And that's that gap I was talking about. But yeah, I'm with you in principle. I don't have a problem with eventually doing everything in simulation, but they've got to get a lot better.
Other questions or comments at this point? Okay, go ahead.
All right, carry on. Thank you. So this is the rest of the talk. I'll start out by describing the world that the agent is in, and you'll see it's a simple world built in the Unity game engine. I'll describe the architecture of the agent. I'll also give some idea of how we train it, go into a little detail about distributed reinforcement learning. I'll then talk about generalization. So this is very important for us because there's a lot of discussion around how neural networks are not very good at generalization. This is often one of the criticisms that's aimed at them. And we have a story here about how we think that even with fairly generic architectures, if you get the training regime and crucially the data right, then actually you can get your networks to generalize in interesting ways. I'll give some examples of that. And then finally, in the last part, I'll talk about how we get our agent to do so-called fast mapping. So this is the problem of learning the referent of a word, effectively zero shot. And then I'll relate this a little bit to how children learn language. So let's talk about the room. So as you can see, it's a single room. It has doors and windows, but at the moment in this version, the agent can't go through the door. We are building some more interesting rooms and apartments and larger buildings, but in this talk, it's just a single room. And it's populated with these everyday objects. You can see they're a little bit unrealistic in size. That's partly because the resolution at which the agent sees is not as high as what you're seeing. So for efficiency reasons, we sort of downsample the image. So I think over time that will improve, and that's one reason why the objects are quite large. But the important thing is there's quite a bit of procedural variation that you can do in the room. So you can, of course, put the objects where you want. You can change their color and size. And that's important so the agent doesn't overfit to sort of incidental properties of the objects. But hopefully you've got some idea of what the room looks like. And I think in these experiments, we have around 50 different types of objects. These are all built in-house. So we set this up as a reinforcement learning problem. Now, ultimately, we want our agents to exhibit the sort of language use that you and I do as humans. So here we're focusing on instruction following, but I certainly don't want to imply that that's all we care about. We want our agents to be able to generate descriptions and ultimately engage in dialogue. So instruction following seems like an obvious place to start because it's very easy to set that up as a reinforcement learning problem. And RL seems like the natural sort of machine learning approach here because we've got an agent that's acting and doing things in the world. So these are the sort of tasks that we define, things like find the teddy bear, lift the helicopter. So the way we set this up is that we program a reward function. So we think that these are all tasks where we can write down a program that tells us, given the state of the game engine, whether the agent has correctly carried out the task or not. Of course, that's, as you know, from a sort of linguistic angle, that's not always true. I mean, even something like, put the teddy bear to the left of the chair. What does left of mean? That's vague. So writing down a hard rule for that is hard, but we do it anyway. I think ultimately we'd probably want to have humans come in and provide some supervision. But here we're assuming that we can always write down a reward function. So we have things like superlatives, find the largest TV, and then perhaps the most interesting task in this talk is the put task, so put a plate on a chair. And what happens is the environment gives the agent a reward of 1 if it carries out the instruction correctly, -1 if it picks up the wrong object, for example, and 0 otherwise. And each episode stops after a certain amount of time. We randomize the room and we come up with another instruction. So that's basically how the agent is taught to follow the instructions. So what about the architecture? I mean, the main thing to say here is very generic. Later on, I'm going to show you, for the last part of the talk, an architecture where we have an explicit memory module. But in this agent, there's nothing particularly special about it. There are no inductive biases on the language side. For example, it's just an LSTM. For the vision, it's just a ConvNet. So there are 2 inputs that go in at each time step, an image, which is what the agent currently sees, the instruction that it receives from the language side. They just get mixed together, so what comes out of the ConvNet and the LSTM gets mixed through an MLP. And then at the top, there's an LSTM, which is kind of acting like a memory. I mean, the way I like to think about this is that in this architecture, it's the place where the agent remembers what it's seen and heard. And the main role of the LSTM at the top is to compute the policy, so that's the pi, and that's just a softmax or a probability distribution over the set of possible actions. And you can see the actions there at the top right, and it's about 30 in this version. So it can move backward, move left, look up and down, grab an object and move at the same time, and also spin an object. So you'll see there's a little bit of motor control in the environment, not a huge amount, certainly not fine-grained, but there is a requirement for the agent to learn how to manipulate objects up to a degree. I'll show you some videos a bit later. So that's the architecture. How do we train it? So we're going to use a form of distributed reinforcement learning. It's called the Impala algorithm. Importance weighted actor-learner architecture. It's a method that came out of DeepMind a few years ago. And I just want to give you a feel for how this works. I'm not going to go into too much detail, but I think for people not familiar with reinforcement learning, it's useful just to get a feel for what's involved in training one of these agents. So this is what we do. First of all, we've got the learner, and that sits on a single GPU. This is going to do a lot of the work with calculating gradients, doing weight updates. So that's computationally very expensive. And then we have a number of actors, and these are going to provide the experience for the learner in order to do those weight updates. And in practice, we're going to have lots of actors. So I think in the experiments we do, we're fortunate we have access to Google compute resources. We might have thousands of these different actors. So what's happening is that the learner's trying to calculate these weights, or the policy, which is the pi w. There's also this value function with the theta parameters. Don't worry about that. I'll just say a little bit about that later. But what we're really trying to do here is calculate the weights for the complete network. So we're going to back propagate all the way through. We're going to learn the convnet, the language LSTM, everything. So we sort of start completely from scratch. So initially what happens is we just randomize the weights. They get fired out to the actors. Each actor has its own copy of the environment and also gets its own instruction. So actor 1 is maybe told, lift up the orange duck. Actor 2 is told to find the tractor. They do their thing, they act. And then at some point, one of them is going to finish, in this case, actor 2. And we've got a choice here, because what we could do is update the weights on the CPUs that the actors live on. But that's expensive. So what we do instead is we send back the trajectories that actor 2 has just carried out. So that's just a sequence of input and action pairs. So the AIs there are the actions that the actor took. We also have to send back the probability of the actions, and you'll see why in a minute. But the important thing here is that we're not doing any weight updates on the actors themselves. We're just passing back the experience or the trajectories onto the learner. And then maybe actor 1 finishes, it passes back its trajectory, and they get all batched up. And then I'll put on a queue, and when the batch is big enough on the GPU, we'll do a gradient calculation and do a weight update. Now, there's a little subtlety here, which is that the actors could all finish at different times. So it might be that actor 2 was particularly quick for some reason, and actor 1 took a long time. So it might be that the trajectory that actor 1 sends back could sit on the queue for a while and be out of sync with the weights that are on the learner. So we have to do a little adjustment that I'll show you in a minute, just to handle the fact that the weights that the actor used can actually be out of sync with those on the GPU. And then what happens after we've got a batch, we've done a gradient calculation, we've updated the weights, we fire them off again, and around we go. Each actor gets a new instruction, sends back its trajectories, and we do that many times. Now, I just want to give you a feel for what the gradient looks like. In fact, I've not even told you what we're optimizing at this point. So this is just the standard value function, that V there. And this is just the standard expected cumulative discounted reward. So basically what we're trying to do is get the agent to get as much reward as possible, as quickly as possible, depending on that gamma discount there on the value of gamma. So how do we do it? Well, if the gradient expression there is just the gradient for a particular action that was taken in one of the trajectories, the AS, so it was an action at time S. So what we'd have to do in practice is calculate gradients across the whole trajectory for all the actions and across the whole batch, but I'm just showing you what it is for one action. And the reason I'm showing you this is it's very intuitive. So basically all it says is that for those weights omega that were sort of intuitively responsible for this action, then what we want to do is update them in the following way. So if the reward we received at time S, you see the RS there, is high or positive, then basically we want to increase the values of those weights, because that was a good action that we took. So the weight should be updated positively. Likewise, if we move into a state at time s plus 1 that has a high value. That's the vs plus 1 you can see at the bottom. And what that means, it's an estimate of how much cumulative reward we're going to get in the future after moving to that state. If that's high, then again, we want to update those weights in a positive fashion. So there's a kind of bootstrapping going on. The v at the end is just the value function. Don't worry about that. This is just a baseline that reduces the variance of the estimate. This is based on Monte Carlo sampling, so you can get high variance. And then finally, the only other thing to tell you about is that row term at the beginning, at the front. And that's defined as the ratio of the probability of the action given the weights that the actor used to the probability of the action given the weights on the learner. And that's just that adjustment I talked about, just to deal with the fact that, you know, if the actor took a long time, then we can be out of sync on the weights. So I'm hoping that just gives you some intuition about how this sample-based distributed RL works. Oh, and incidentally, for any sort of RL aficionados in the audience, the gradient at the bottom is just the more or less the standard policy gradient from the reinforced algorithm. There's nothing special about that at all. You can read about it in an RL textbook. So this is what happens when we train the agent. So you can see the room there, it's doing the lift task. You can see here we trained it on 3 tasks at the same time. So it's kind of a curriculum. The idea is that if we want the agent to put an X on a Y, then it's got to know how to lift an X. So it turns out to be useful to train the agent on those at the same time. You'll see a lot of these plots. What's happening here is on the Y-axis, you're getting the reward. So this is what's happening during training. And we want those curves to get all the way up to 1.0. That means that it's basically solved the task. You can see that for 2 of them it does, and we're not quite sure why they put an X near a Y. It doesn't get all the way up to 1, but it does pretty well. And then the interesting thing, if you look on the X-axis, is how many steps you need. It's very expensive, this training. So this it's taking over 1 billion steps to even learn something simple like this lift and put task.
Can I ask a question?
Yeah, please do. Yeah.
The task. No, you can leave on the. Put. It seems obvious that put an X near a Y is a matter of degree, whereas put an X on a Y and lift an X is all or none.
Yeah, that might be the problem. So as I said earlier, it might be that although I don't know. I mean, we would have hard coded what it means to be near. You know, it would be something like you have to be within half a meter of the Y. So I don't see why it couldn't learn that, actually. So given that we've hard-coded it, it has to just go and learn that hard-coded function.
There was also a question earlier with the prior speaker. He was very good at time sharing and looking at the written questions. But let me just read you another question that came out. We're setting up your simulated world from Mao. Would setting the room in a meaningful way limit how much prediction an agent has to do at any given point, specifically as embodiment entails affordances defined through constructed actions, right? Embodiment means empathy with other actors. Would observation of actions by other agents help you limit how many instructions you have to hard code? That's actually 2 questions.
Oh, well, to answer the last one, definitely. Yeah, I mean, I guess something else we think about a lot is trying to do this through imitation rather than reinforcement learning. So have a human come in, or even a scripted bot actually, and do the lifting task. So give the agent some examples of what it means to lift, and then have the agent copy that through imitation learning. So that would definitely be more efficient. That's something we think about. I think I wasn't quite sure about the first question, but let me try and answer it. So there's definitely a sense in which the complexity of what we have in the room is absolutely crucial, obviously. And at the moment, it's very simple. So in particular, we don't have a lot of tools. The objects don't really have any interesting affordances. And that then relies on our software engineers who build the environment to produce that for us. So we're very much reliant on them giving us an interesting room, and that's something that's ongoing. So I hope that answered the question. I think maybe the short answer is there's not a lot of embodiment at the moment, but it's something that we're working on.
Okay, that's fine. Go ahead, please.
Thank you. Oh, and here it is doing the putting, yeah. So put a bus on the storage tray. I think the reason I wanted to show this video in particular was because you get a little bit of an idea for the sort of control that's required. As I said, not a lot, and there's no affordances or tool use at the moment. But it's going to try and pick up a cup or a mug in a minute, and it'll struggle a little bit because it's so large. Here we go, this one. So you see it really struggles with it. So there's a little bit of control required there to get the thing to balance on the bed. I mean, eventually, just to go back to my previous comment, we'd really like kitchens and rooms where you can drink tea in a cup and have liquids and all those sorts of things. But obviously, simulating that is very hard. All right, so that was the first part. So let me get on now to the second part, which is about generalization. And what we're going to do is try and get the agent to carry out instructions that it's never seen before. So zero shot, although of course it's going to be made up of parts that it has seen. So it's going to be, maybe we could even talk about compositionality involved in following the instructions. And just to give a bit of historical context, we relate this to the debate, the classical debate now on systematicity. So this goes back at least to a paper, a classic paper by Fodor and Pilishin, where they define systematicity, although, I mean, it's a fairly loose definition, I have to say, and there aren't a lot of examples in the paper. But the intuition is the idea that any human who knows the meaning of Alice loves Bob surely knows the meaning of Bob loves Alice. That's their example in the paper. So the ability to entertain a given thought implies the ability to entertain thoughts with semantically related contents. Now, they're not entirely clear about what semantically related means either, but sure, I mean, you will get the intuition. And the claim is that neural networks are very bad at exhibiting this sort of systematicity because they tend to overfit to the data. And then, people like Gary Marcus these days will argue that the way to deal with that is to have an explicit recursive rule-based system. That's essentially what they're arguing for. Whereas on the other side, we have people like Jay McClelland and our DeepMind colleague, Matt Botvinnik, who argue that, actually, if you get the training regime right and think about the correct inductive biases, then surely neural networks can exhibit systematicity as well. And we're going to try and just add a little bit to that debate on the side, I should say, of the connectionists. So here's how one experiment in which we try and do that. So we're going to have a training regime where we train the agent to lift an object from this set on the left. And crucially, it's the union of the ones in blue and the ones in red. So we train it to lift a boat, a keyboard, and also a plate and a roof block. And then we'll train it to do the putting task, but this time on just a subset, the ones in blue. So we'll train it to put a boat on a bed or a tray, put a keyboard on a tray, put a rocket on a bed. And then we can do this hold-out test where we ask the agent to put a hairdryer on a bed. And crucially, it's not been taught how to do that. So it knows how to lift a hairdryer, and it knows how to put a boat on a bed, for example, but never a hairdryer. It's never been taught to do it. And this is what happens. So it does it pretty well, not perfectly. So the one in orange is the training curve. So this is we know already that it can do the put task. And in test, it gets to about 90%. So in the video, I think these are zero shot. It's never been trained to put a roof block on the storage tray, for example, but it's been trained to lift a roof block. So we think this is an example, albeit somewhat limited, of the agent exhibiting systematic generalization. And I think our main claim, and this is a claim I'll repeat again later, is that it really depends on how you train your agent, both what the training regime is in terms of the data that it sees, and also a little bit around architecture. So we're going to see a little bit of inductive bias a bit later. But it doesn't really make sense to say that neural networks cannot exhibit systematic behavior. It all depends how you train them. Now, we'd like to know what the factors are that contribute to this behavior. And in the corresponding paper, we look at a few things. In the talk today, I'm just going to talk about the number of word types or objects that are observed during training. So this turns out to be important for this particular setup. In the paper, we also look at the importance of active perception over time, just the fact that the agent can move around in the room and decide what it looks at. And it also turns out that the first person agent-like perspective is important as well. So looking at the number of word types, we have a slightly different task this time. We're going to have some negation. So similar to before, this time the find task. So during training, what we do is we get the agent to find a boat, a keyboard, a plate, and a roof block. So again, it's the union of the ones in blue and red. And then we have this task where there's a not. So we say, we train the agent to find something that is not a boat, not a keyboard. And again, we hold out the ones in red. And then at test time, we say, can the agent find something that is not a plate? And it's not been trained to do that. And interestingly, well, it depends. Sometimes it can do this and sometimes it can't. And it all depends on how many types, object types, you've shown the agent during training. So I think chance performance here is a half, because I think in this setup, it was just choosing between one of two objects. So you'd have a plant pot and a roof block, and you'd say, find the object that is not a roof block. And interestingly, if you train with only 5 types, if the agent's only ever seen 5 types, it's actually worse than chance. So if you tell it to find an object that is not a roof block, it'll go and pick up the roof block. But if you increase the number of objects, in particular, we use ShapeNet, which is an external repository of Unity assets, around 200 shapes, you can improve the performance significantly. Again, not all the way up to 1, but in this case, up to 80%. And I've got a sort of hand-wavy argument for why this might be happening. We think what's going on is that if you think about negation sort of logically, then it's the set complement. So if you want to know, what is not a roof block, well, it's everything that's remaining in the universal set of objects. And we think that the agent doesn't get a good feel for that notion of set complement if you only give it 5 shapes. So if you show it 200 and give it lots of examples of things that are not roof blocks, then it sort of learns to know what negation is in this very limited context. I mean, admittedly, that's a bit hand-wavy, but that's my intuition. Yeah, so just to conclude that part, I think I've said this already, but we think that systematicity and some element of compositionality can emerge, but it really depends on the training environment, the regime, and the data. So that's what's important. So maybe I'll just stop there again, Stephen, and see if there are any questions at that point.
Do you want to say your question aloud? No, you want to say your question aloud?
Well, thank you, but
okay, well,
it wasn't a question. It was just to say that it was just a comment from the prior thing. So no, thank you.
Okay, Elizabeth?
Yeah, great question. So first of all, we definitely have variety in color and shape. No, it's color and size, I'm sorry. So the plane is not always the same color, and we vary the size of it slightly. So that sort of thing turns out to be important, so the agent gets some variety. In terms of whether we have different planes, I think at the moment, this particular set was built in-house, and building them is quite expensive, so we probably only have one plane. But we've done some experiments with ShapeNet, which is this, as I said, this freely available set of assets, and there might be 100 different planes. So it really depends on which experiment we're doing. I think everything I've shown you so far, there's only one plane, there's one table and one chair. But of course, eventually we'd want as many of those as we can get our hands on. We don't want, yeah, it's a great question, thank you.
Other questions? You mentioned that generalization is one of the tricky bits in this kind of thing, and how, if you use objects and what you call them objects, but in fact you just have one exemplars, you can hardly expect a generalization. It seems to me that generalization should be trained from the very bottom up, which is that you're picking up kinds of things and not individuals.
Yes, I absolutely agree completely. I mean, of course we want the agent to get a general notion of what a car is and a vehicle, and to do that you've presumably got to see quite a few cars. Although interestingly, my understanding is that human children are actually quite good at doing that generalization even after only seeing 1 or 2 cars. Isn't that true?
Yes, but it's true, but it's because they see a hell of a lot of kinds of things, and they're not all that different, so there's generalization going on all the time.
Yeah, so I absolutely agree. And again, it all comes down to the limitations of the environment and how difficult it is to build these environments.
In fact, that's the bottom line on I asked you about simulating in simulated environments. A simulated environment is as good as your simulation of the environment, right? You're trying to simulate the agent, but in fact, everything depends on how veridical the environment is. And that's the one little question I want to ask, which is always niggling, which is, these are all toy situations. What's the difference between a toy situation and a generalization? I mean, a good enough mathematician could look at your setup and could say in advance, without doing any simulations, what was going to happen, because it's just finite and it's combinatory.
Oh, well, I'm not sure about that. I mean, it depends which elements you think are finite and combinatory. So in the sense that we've only got one chair, that's obviously finite. But there's a lot of procedural variation in where the objects are placed, their colors, and we could easily, you know, change the color of the floor and the wall. So I think one thing that's always at the back of our mind when we're developing tasks and environments is this element of procedural variation that you're talking about. And that's so crucial for neural networks because they're so good at exploiting, you know, the tiniest little signal that you wouldn't imagine as a designer. So I'm not sure. I mean, I agree that the combinatorics is challenging to get right, but I think we can do it. Does that satisfy? Are you worried that we'll just never get the combinatorics that we need?
If your goal is Turing test level capacity, robotic Turing test level capacity, the world is really big. And these little tasks are very small.
Sure. So again, I think there, you know, our argument would be that we started with a room. In fact, we call it the playroom because we're inspired by a sort of human learning curriculum. And the child starts out in the playroom. And, you know, what I'd really like in a few years' time is to come back and give this talk and we've got a whole apartment. And then a few years after that, come back and we've got a park and a city. But sure, there's a question mark about how easy it is to develop those sorts of environments, but that's the goal.
Well, we'll certainly keep inviting you back.
Okay, all right.
Go ahead, please.
I have a question. Thanks. This stuff you're doing seems to make the case for an argument that you weren't willing to make before, which was GPT, BERT, those models which are all trained on text are potentially missing some kind of semantic information because of the way they're trained and the modalities that they're, well, the one modality that they're trained on. And you get a lot of heavy lifting from those. They go really far. You can do translation, you can do all kinds of text-related tasks. But from what I'm seeing from this research that you're showing us, these results, is that being embedded in the environment matters when you're learning pick up versus put or those kinds of things. It matters how those interplay with each other and will ultimately matter to AGI. I think that's what you're getting at with this.
Yeah.
But I have other questions about virtual worlds versus robots, but I'll save those to the end.
Oh, okay, thank you. And I agree entirely with your point. I mean, as I said, my answer to that is somewhat mundane in that, you know, if you want a robot to lift the teddy bear, or let me put it another way, it doesn't matter how many car manuals you feed to GPT-3, it's never going to be able to drive your car.
Right.
Just in a trivial sense, that's all. Now, whether there's more to be said along those lines in a more philosophical way, I'm not sure. But my reason for grounded language learning is just because of what we want to do. Now, I'm sure there's more to be said there that's more interesting around the role of embodiment in language learning, particularly in humans. But at the moment, my feeling is if you want to build a summarization system, then don't bother looking at embodiment, just get lots of data.
Right. Okay, that's good for now. Thanks.
All right, thank you. Okay, so I'll move on to the last part. So this is about, solving the so-called fast mapping problem. I think I've got a video, first of all, showing a child. Children are very good at a certain age of doing this fast mapping. Here we go.
Look at this. Look, it's the Toma. 13-month-old Max is invited to the lab. Dr. Woodward and researcher Ashley Brown show him an object with an invented name. Wow, it's the Toma. Do you see? Look, it's the Toma. Both researchers are looking at and pointing to the object when Ashley says the name. Look, where's the Toma? Can you get the Toma? Then Max is asked to pick out the Toma. Good job. You got the Toma. Yay. Good work.
So there you go. So you saw that the child was able to pick out the Toma. We call this the DAX task because often the nonsense word that's used in these experiments is DAX. And this is something that children are very good at from that age. You know, they can immediately bind a nonsense word to this new object. The child's probably never seen the Toma before, and retrieve it. And we wanted to see whether this is something that our agent could do, because I think this sort of fast binding is typically very difficult for neural networks. And you've seen how many training experiences it needed before just to find an object or lift it. So what we did was we set up a simulated DAX task, just like you've seen the child carrying out. So in our room, we'll have the agent move around. And what happens is when it moves up to an object, there's now this linguistic description that comes from the environment. So it's told this is a DAX, this is a Blickit. Then after a certain amount of time, after a minute or two, we'll randomize the positions of the objects in the room. And then it's told to pick up a Blickit. So the first one we call the discovery phase, the second one the instruction phase. And if the agent then goes and picks up the star-shaped object, in this case, he'll get a positive reward. And if it picks up the cloud-shaped object, he'll get a negative reward. That's basically how we set it up. For the default setting, we also have a little bit of a shaping reward just to make things easier. So every time the agent goes up to any object, it gets a little bit of reward, say 0.1, just to encourage it to go and look at objects in the discovery phase. So that's how the task is set up. So here's a picture in the room. So I think in the top left, you can assume that the agent is looking at the pink book. So in this episode, that's called a DAX. Now, the way it's set up in later episodes, if it sees a pink book, it'll be called something else. That might be the Blickit or the Feeble. So the word DAX only applies to the book on this particular episode. And in this case, it's told to pick up a Feeble, which was the plant pot. So if it goes and does that, it'll get a positive reward. That's how the training works. Now, our intuition with this was that actually our vanilla agent wouldn't be very good at solving it. In fact, that turned out to be the case. So we wanted to put an explicit memory module in, and we're partly inspired by the literature on meta-learning. Or let me just say why I've described this as a meta-learning task, first of all. It's meta-learning only in the sense that there's this sort of inner and outer loop that's characteristic of meta-learning. So what I mean by that is that for a single episode, you can think of that as the inner loop where the agent is learning the meanings of the words. So this is a sort of learning to learn setup. So on each episode, it has to learn these words zero shot. But then if you think about the outer loop, that's the loop that's going over all the episodes. That's where it's doing the learning of the learning to learn. So that's the only sense in which I mean meta-learning. And if you look at some of the literature on meta-learning, so Santoro et al. In the Omniglot data set and Brandon Lake with SCAN, I think they found that an explicit memory module is very helpful. So we wanted to put a memory module into our agent, and this is how we did it. So we call it the dual coding episodic memory, after the dual coding theory from Pavio. So I'm a little bit out of my comfort zone talking about this, but my understanding is that this is a theory of neuroscience coding where different modalities are coded differently in the brain. So we're taking inspiration from that, and the idea is very simple. We're going to have a key value memory where, in our case, the key is going to be language. That's a language embedding that's going to come out of our LSTM, and the value is going to be a vision embedding. So that's what comes out of the ConvNet. So if we just go back, the intuition, maybe all the way back here, is going to be that when the agent sees this is a Feeble, let's say, it'll put the embedding of the language in the memory, and right next to it, it'll have an embedding of what it sees. And then the idea is that during the instruction phase, if it sees pick up a Feeble, it can encode the instruction, go and look in the memory on the language side, which is the key. And if the thing that it retrieves looks like what it's looking at now, then that's, an indicator that perhaps it ought to pick it up. That's the intuition behind what we wanted to build. So this is what the architecture looks like. Now, of course, whether that intuition really cashes out in the computation of the agent, who knows? It's just this neural network doing its thing. But we're putting a fairly strong inductive bias, I would say, into the architecture here to encourage it to use the key value memory. So just to repeat what I said, when it's told to lift a DAX, that gets embedded by the LSTM, some transformation of that into a query. We compare that with all the keys on the language side in our memory. We extract the top K just through some similarity metric, only on the visual side. So these intuitively are all the things that look like DAXs. That passes into the agent core. And as I said, the intuition is the agent can then compare that with what it's looking at and decide whether to lift the object or not. So just to compare with other architectures, the LSTM is just the vanilla architecture I showed you right at the beginning. There's no external memory at all, everything in what we might call working memory. We also looked at the differentiable neural computer, or the DNC. This does have an external memory, but it's content addressable. So there's no explicit key value system. This is a strong intuition we have that separating those two modalities is very useful. Of course, we also did a transformer. So the way the transformer works in this case is that the way to think about it is that you take an episode of experience, which is just a sequence of language vision pairs, so everything that it's seen and heard in its experience so far, and just stick a transformer on top of that, basically, with its self-attention mechanism. So the transformer kind of has an external memory in that the attention mechanism itself has keys and values, but those are learned. There's no explicit pairing of the keys and values in the way that we do in our memory. But it's quite similar in high-level motivation. And then we've got the dual coding episodic memory that I've just described, where the modalities crucially play the key and value roles. Oh, incidentally, I mean, you could imagine problems where you'd maybe want to reverse that. Maybe you'd want the vision to be the key and the language to be the value, or even some mixture. But I think for us with this task, it's pretty clear that it makes sense to have the language as the key and the vision as the value. And this is what happens. So this is a 3-object DAX task. By that I mean that there are 3 objects in the room. And the LSTM, the vanilla architecture, doesn't solve it at all. So I think the take-home message here is really that our DSEM agent and the transformer both solve the task. So the curves on the right, they look a bit fuzzy because we always do sweeps over various hyperparameter values, and the bold line in the middle is the average. So you can see the red and purple curves are going right to the top. They basically solve it. And there's also a plus recons there. So there's an element to this I haven't told you about, which is that if I just go back, in this architecture, just above the embed and the CNN components, we have some representation learning. So on the visual side, we essentially have a sort of reverse convnet where we get the agent to, from the embedding, to recreate the image as a kind of representation learning. That's a fairly standard trick these days in this sort of architecture. And it turns out that that's helpful. That's what I mean when I've got the plus the recons. But the take-home message here really is that the 2 agents that had the explicit memory are able to solve the task. Now, maybe we can talk later about, do we really need the DSEM? Why don't we just do everything with transformer? But I'm not going to say any more about transformers in the rest of the talk. So here's a bit more generalization. So let me talk about the curve on the far right first of all. So what I've done here is we've got an experiment where the test or the trials are always with 8 objects. So there are 8 objects in the room. They all get these nonsense names, and one of them's the DAX, and you're told to find the DAX. But the key point is that in the red curve, where the agent doesn't solve the task, it was only trained on 3 objects. So there's a sense in which it's sort of overfitted to the 3-ness of the training. But the interesting one is the green curve, because there we get a bit of generalization. So we can train on 5 objects, and the agent will still be able to do the task with 8. Same story, the one in the middle, in that the red curve is a failure case. We don't really generalize well from 3 to 5. And then the one on the left, it's just not surprising that if you train on more objects than at test time, you can still do the task. So the really interesting story here, I think, is the green curve on the far right, where we see a little bit of generalization. We also looked at whether the agent was getting a general notion of object in the following sense. So the training here is going to have objects like the the cloud and the star. And of course, in the room, it'll be the objects that I've shown you, but just for an example. And then at test time or during evaluation, we'll get the agent to do the DAX task. But this time we'll introduce objects it's not seen. So this sort of bed-like, it's a bit like a bed. This is a DAX and the circle with the line through it. And then we'll ask the agent to pick up a blicked. So it's these nonsense words it's seen before, and it knows how to bind them, but it's never seen this particular set of objects. So the way that we do that in practice is that we just hold out 10 objects from our set. So this, might be a bed, a plant pot, a roof block. So the agent's never seen those before. And then it's trained on the remainder. And it turns out that the really crucial bit here, again, is how many objects does it see during training. So if it only sees 3, and maybe this goes back to a point I think Stephen was making earlier about the variety of experience, then it's not very good at doing the task on these 10 objects it's never seen before. But if you get up to 5 and certainly 20 object types in the training set, then it starts to do very well. Again, not perfect, but we're getting up to sort of 90% accuracy. So again, it's just this message that the training regime matters. Maybe not so surprising. And then just got one last part, so I think maybe I'll stop there again and see if there are any more questions.
I have several, actually, if that would be okay.
Oh, great, yeah, go ahead.
So the first thing is, I was wondering if you considered the structure of language as it pertained to position in the room. So for instance, this and that entail 2 different positions in relation to positions in the room. Is that taken into consideration?
Yeah, we haven't really looked at words like this and that. So you mean it'd be something like, what would an instruction be? Oh, I see. So this is a DAX, that is a DAX.
Exactly, or pick up this DAX, or pick up that. Yeah. That also entails like a common shared vision, right? Orientation.
Yeah, and we'd love to do that. There's something we think about. We don't have that in these particular experiments. So it's very simple in the sense that the agent always gets this is a DAX when it's immediately looking at it. But you could also imagine, we'll talk about having sort of pointers in the room as well, a virtual pointer pointing at something and saying that's the DAX. Yeah, great idea. We've not done it yet. Did you have any more questions?
I did, but there are other people, and I don't want to hog, but if it circles back, I'll ask my other question.
Someone else want to ask a question first? Otherwise, Mao, it's still yours.
Okay, then.
Yeah.
Oh, sorry.
Did some say, I can't see everybody at one time. Could you just for a second unshare, Stephen, then I could see everybody. Okay, so just let me know by waving your hand or something that you want to ask. If not, Mao, go ahead.
All right, so you mentioned that it seemed logical to you that the word would be the key and that the object would be the value, right? So it's it's very object oriented. I wanted to run by you the idea that while words are indeed limited, so it means that there can be several meanings to a word, images and objects are way more rich in terms of the linguistic possibilities that they allow. So it seems to me like the visual field should be the key, and the value should be a series of possible words with weights in relation to a specific situation.
Ah, interesting. Yeah, I mean, it may well be that the task that we've set up is particularly simplistic, so that it really relies on the key value setup that I've talked about. But yeah, you're absolutely right. I could definitely imagine other tasks, maybe more realistic, where you'd want it the other way around, or maybe a mixture. And I think we'd see that as a strength of our proposal, actually, that it's very easy with that key value mechanism to have either the language or the vision as the key or the value. So I agree. Okay, so I share again and
Sure.
get the last part done. Yeah, so this is all about, as we say, language learning fast and slow. So the idea here is that what we'd like is the agent to follow instructions like we've got on the right. So we want things like put the blicket on the bed. And the key point here is that the bed has been learned in a slow way, in the sense that the meaning of bed is just its everyday meaning. It doesn't change every episode, unlike blicket. And this is a little bit more realistic. I mean, still we're a long way from the realism of how children learn language, but we're getting a little closer. So I wanted to see whether the agent could integrate fast and slow knowledge at the same time. Yeah, so this is the idea. Again, we're going to have these objects that we call DAX and blicket, but we're going to have two objects in the room all the time. In this case, it's going to be a bed and a box or a tray, and they always have the same name. So that's the slow or semantic knowledge, if you like. And the story is that, yes, we can get the agent to do that. So the number at the top, the 0.97, is when the agent does it almost perfectly. And what we do there is we essentially set the training up in the simplest way possible. So the agent is trained to basically do the task. But I think the more interesting one is what we're calling the minimal training regime, where we get not perfect accuracy again, 68%, but way above chance. And here's how we do it. So there's a little bit of generalization going on again. That's the idea. So we're going to teach the agent to do the fast mapping task as before with lifting. So if we go right, if we look at the top on the left with the task name, we've got this is a DAX, and we'll say pick up a DAX. So that's how it learns to do the fast binding. We'll also do a slow lifting task, where in this case, we're teaching it the meaning of car and horse. And we'll also do a slow putting task. So this is a car, put a car on the bed. And then finally, just the evaluation. So when the agent is never trained to do this, we'll say this is a DAX, and we'll ask it to put a DAX on the bed. So it's doing that zero shot in the sense that it's never mixed the fast and the slow learning in that particular way. And that's where we get the 68% from. And I think this is an example of the agent doing that. So you can see there's the bed and the tray, they always get the same names. But all the other objects get these nonsense names that are different every episode. So it's going around, it's getting the names of the objects. And I think there might be a failure case in this at the end as well. So sometimes, as you saw, it's not perfect, certainly in the 68% case. We haven't done a lot of analysis of why it gets things wrong or when. So I'm not really sure why in this particular case it just picks up the wrong object. But that's an example again of how it can do some generalization in this really interesting case of combining the fast and the slow learning. Now, from a human learning perspective, there's something slightly odd about this, which is that, because when the agent has learned the meaning of the word DAX, it immediately discards that meaning, because the way we've set the thing up. It has to learn DAX refers to something else in the next episode. So one interesting extension of this work that we're currently thinking about is how to do fast learning that ends up being long-term semantic knowledge. So can we show the agent just one or two examples of chairs and then have it know what the word chair refers to? So that would be the obvious next step. So that's it. So thanks for listening. Just to conclude, what have we shown? Well, I think we've shown an example of grounding in a simulated environment that's I think very exciting for me. If we compare it with something like purely text-based NLP, I think what's really very different about this work is the fact that we have the agent interacting with this environment. And we've also had this story about how we think the agents can exhibit some form of systematic generalization, but crucially given the right training regime. And then finally, we had the experiments on how the agent can do fast mapping and also combine it with slow learning of words. So I just want to acknowledge some of my collaborators, a number of people at DeepMind who've worked on this, but in particular Felix Hill, who's my main colleague at DeepMind, who I work with on all of these experiments. And if you want to go and read about it, there's a number of papers that are linked from my webpage. Yeah, so thanks again for the opportunity to talk, and I'm happy to take some more questions.
Thanks very much. Ken, maybe you could unshare and then we can see faces again.
Yeah.
That's it. Thank you very much for your talk. I don't want to hog this, so let's have questions from other people. Otherwise, you're...
Picard wrote a question.
Yes. Well, why don't you read it?
I think I can look at the chat now myself as well. Let me see. So is the one right at the bottom. So the graph you showed on the previous slide has an inflection point. Oh yeah, we sometimes get inflection points because one not very interesting reason is that if you remember, I said that we have this little shaping reward where we give an agent 0.1, for example, every time it goes up to an object. So what you tend to see is that initially the agent will learn how to go up to each object and it gets a little bit of reward, that's the inflection. And then after it's done that, it has to learn to do the fast binding. So I think the answer is not very interesting, actually. It's just the way that we've set up that particular task.
Other questions? Casey, or you have a follow-up? Yeah.
I do. I have a couple, but I'll just do one at a time here. The interaction with the environment, I think of is obviously the right direction to go when you're talking about, or when you're making any claim about, we want to teach these things like children are learning. But what you're doing with the agent is, it's not a human-to-human interaction. It's the agents being told what to do, which I have some kids and I've seen Childees. You don't do that all day and just have children do navigation tasks and pick this up and put that there. Though I understand the constraints on the task for doing the things that you're doing. I think that's fine. But one thing I really want to know is when we're talking about children learning language and they're interacting with their environment and with other people, what's the supervision signal in the environment that helps them know that this word refers to this or that this word refers to that? Because you're using a reinforcement learning signal, but it's not obviously the one that kids are using. It's one that you're giving these numbers to the system when it does something right or when it does something wrong, and it's kind of arbitrary based on the task that you're doing. Can you say something about that?
Yeah, I mean, I agree. I mean, there's almost a sense that I like the way you put it. It's almost like the environment, some sort of God providing this godlike thing, sort of giving the supervision and saying whether the agent has done it right. So I think eventually we might move away from this reinforcement learning idea entirely. It just seemed like an obvious place to start. Maybe it could serve a useful form of bootstrapping, when we get to the point where we've got hopefully humans interacting with the agent. I mean, there's another reason to doubt whether this could take us all the way, which is this idea again of how hard it is to write down a programmatic reward function. I mean, that's just going to be impossible ultimately. We can't teach, we can't write down the correct behavior for every single thing we want the agent to do. So I think that alone is a reason why we need something better along the lines you were suggesting.
I think you're right. And just to follow up, that's the wrong way to look at it. The only thing I found in the child development literature, and I know there's a lot of better child development cognitive scientists in this meeting than I am. I'm not a cognitive scientist, but they just want to interact. That's it. And then that's if that happens, then they're happy and they learn as a byproduct of that, it seems. But that's not kind of the way the field is going in any type of fashion. But I'll be quiet now.
Yeah, I think I can safely say there, just from the point of work that's happening at DeepMind, that I think there's a technical report about to come out in the next month or so that I didn't talk about, that has the playroom I described with a lot more interaction, including some interaction with humans. So I think we agree absolutely with everything that you've said, which I'm just not at the point yet where I can, give you the research. So I think that's the direction that we're heading in. Yeah, I agree entirely.
What's the connection with Google?
Oh, you mean what's the connection of DeepMind and Google, or just from an organization perspective?
Yeah.
So, yeah, the connection is that a few years ago, Google was restructured into something called Alphabet that now sits at the top. That's the company that Google sits underneath. And then alongside Google, there are these companies called, and they literally call them bets. And DeepMind's one example of that. So there are other bets that work on self-driving cars and so on. So that's the connection. We sort of sit alongside. But the important thing from our perspective is that we're very lucky we get access to the Google infrastructure. So it allows us to do all these experiments that, as you've seen, are computationally very expensive.
No, I'd agree to being called a bet if I had that, for sure.
Yeah.
Okay. Go ahead, Matthew.
Yeah, so you started off the talk talking about how dictionary-based methods are very impressive, but they have certain limitations, and then you started describing your work in I guess, embodied understanding. I'm just wondering, have you thought about how to combine dictionary-based methods with this sort of simulation-based understanding, and how you could test whether or not the understanding has actually improved?
Yeah, absolutely. I think you can think of that in two directions, right? So one direction would be to say, can we build better translation systems if we've got an embodied system? And I guess in the past, people thought that to do really good translation, you'd need proper understanding. And as I said, I think current NLP systems are arguably counterexamples to that. But you can go in the other direction and think to yourself, how can I leverage the power of these large-scale language models to do better situated and embodied learning? I think that direction is quite interesting. So there are people now in NLP, probing language models for common sense knowledge. They seem to know so much stuff, and maybe you could try and ground some of that knowledge that's purely text-based and have that be useful to the agent. So that's the direction we're thinking about at the moment.
Casey, did you have a follow-up from your prior question?
Yeah, it was more about the robot stuff. So I've seen different researchers kind of do this. They might start in a virtual environment, move to robots, or they might start with some toy robot and decide this is too much, I want to move into a virtual environment. Why not? I mean, and you mentioned, well, we want to expand this little toy scene with this kind of finite set of states to at a park, add lots of different things. At some point, I don't know, maybe they have a backstory or children or something like that, right? These agents have this real life that you're trying to throw at them or build on them. Why not just use a robot in that case? If you're gonna, robots are hard, I get that.
Yeah.
But why constrain it to this environment and kind of work where it's easier on some of the problems that are important, as opposed to actually putting it in the physical body and having it work in a real environment and look at real objects with real pictures and have real manipulators?
Yes, I think there's nothing to stop us doing that. And we do have quite a big robotics group at DeepMind. I guess there are trade-offs, aren't there? It depends, I think, what's the question you want to ask. So in particular, robotics, I mean, you will know better than I do, but there's a lot of work on, say, fine-grained control, isn't there? That's an important thing. Just getting the robot to pick up the cube is really hard, and tie shoelaces and all that. We're not so interested in that, I think, because arguably it's less connected to the language side, where you're already at a sort of high level of abstraction. And I guess the other thing is that if you want to increase the complexity of the room and go to the park or the apartment, it's just so much easier to do that in simulation. So I can see arguments for going both ways. It depends what you want to do, I think.
I have a response.
Yeah, go for it.
I mean, if it is difficult for robots to do these fine-grained motor control and pick stuff up, but that's where grounding, I think, really plays an important part, because, I mean, we know about mirror neurons, we know about all kinds of stuff where it's not just how the object looks, but it's how your hand might fit around it, or the affordances of the object that you have based on how you can interact with it that are tied to language. It's there is an abstraction there, and Stephen can say a lot more about that than I can, but I think the meaning of something is the affordances of it and how you interact with it, and how it, not just how it looks, but how it feels, how heavy it is, all those things.
Sure.
Okay.
Yeah, so I agree with that. And again, I mean, ultimately, we'd want to do both, wouldn't we? And maybe cooking's a nice example. Think about following recipes. You can either think about the affordances of the knife and chopping something and go reality in sort of that direction, or you can think about the high-level plan of following a recipe and the order in which you put the ingredients together. And they feel like sort of different problems to me. And we'd like to be able to do both, but at the moment, the best we can manage in this simulator is not a very good simulation of what it means to cut something. So perhaps that's the place where you'd want to go to the robot.
I wonder whether the child experiment that you showed a little cameo of, the child being shown the objects and then learning to associate the name with the named object. I wonder whether that's misleadingly simplistic in the sense that I don't even know whether we should look at what it is that parents do with pre-verbal children as our model. We should look at non-human species, because non-human species have a lot of interaction with the environment. They also learn what things are and what to do with them. And surely that precedes any of this. The idea that you have somebody in there getting orders as to put it on the table, put it on the bed, that's sort of, that may not be the right entry point. And one of the things that all mammals who see have is they're already born with object constancy. So for example, if they look at a thing, they don't have to learn that that thing is the same thing when it just, its orientation changes a little bit, et cetera, et cetera. They've got all that for free. But there's a lot of affordances that non-human species have to learn, affordances that they don't have for free. And my own intuition is that it's dealing with these and generalizations over these that really give you the bedrock for when we start talking about language and naming. Yeah,
I mean, there are people who follow that line at DeepMind as well, that, you know, we really should worry about conceptual understanding first and building object representations and doing all the things you described and then put the language in. I think just because I'm coming at it from a language perspective, and I think that potentially there's an awful lot that we can get from large scale language models, for example, I'm interested in just sticking language in from the beginning and almost bootstrapping and seeing how much we can get from the linguistic signal. But I agree that that might not be biologically realistic or plausible.
Well, are there further questions? We've covered a lot of territory. I have more questions, but I don't want to keep everybody here for those. I just want to thank you then, Stephen, for coming all the way to Montreal for this.
Yeah, I'm sorry I can't be there. I would have liked to have come to Montreal.
And but if there are any follow-up questions, is it all right if people email you?
Of course, no, that'd be great, yeah. And thank you so much for the invitation and all the questions. It's been really fantastic.
Okay, and thanks to everybody. Next week, it's Friedemann Pulvermüller. And maybe you'll be interested in that actually, because it's going to be trying to do grounding with a more neurobiological motivation.
Oh yeah, I might well come along to one of the next two for sure. Yeah, so I'll see you again.
Okay, thanks everybody for coming.
Thank you, bye-bye.
Bye-bye.